So we're going to talk about porting OpenMandriva to many different CPU architectures and giving a couple of hints about what you can do and what you can avoid when you are porting something else from one CPU architecture to many. I know that yesterday we've had a couple of problems with some people speaking so fast that the translators couldn't catch up, so if anyone is listening to the translation, please give me a sign if I'm talking too fast. But let's get started. So I'm not sure if everyone knows what OpenMandriva is. We are one of the oldest Linux distributions out there. We started 1998, back then called Mandrake, then got renamed to Mandriva after merging with the Connectiva Linux distribution from Brazil. And then when Mandriva, the company, went out of business back in 2012, we turned it into a community project and called it OpenMandriva. The business is gone, but the community is still very much active and making new releases with 4.0 coming up hopefully later this year. We have always primarily, but not exclusively, been desktop OS, which of course, given available hardware up until very recently meant having a clear focus on x86. But with the upcoming version 4.0, that is changing. We're going to release that version for still x86, but also RISC-64 and ARMv7 HNL. And Ryzen, which is a special variant of x86, that's the latest AMD processors. You can run the generic x86 version on those processors, but we found that tuning the distribution specifically to the Ryzen processors gives us a 15% speed boost. So that's worth doing as a separate architecture as well. And we are currently working on porting to the new completely open RISC-V CPU architecture. That's not going to be released with 4.0 because it's just not ready, but some initial early builds should be available for testing soon. So why are we doing this now? The first point is obviously some other CPU architectures, especially RISC-64, are getting fast enough to replace a traditional desktop. If you have a half-decent RISC-64 machine, a Cortex-A53 or A75 even, you can run all the normal desktop applications on it without really noticing you're on what is supposed to be a slow machine. Then clearly monopolies are always harmful. We want variety of CPU architectures to exist instead of just one. And there's increasing concerns with Intel and AMD processors about the Intel management engine and AMD's equivalent of it, which is essentially a separate processor built into the processor you are using that can control things even while the computer is turned off, and that has access to all the hardware, so certain agencies could abuse that to get access to your data. And we think it's important that desktop systems become available on hardware that don't have this sort of functionality built in, even if nobody is using that functionality right now. We don't know that someone is using it, but we know that it's very much possible someone could start using it that way. So the pictures you see there are actually RISC-64 devices that we think can replace the traditional desktop. The laptop based on a RASPad. In the middle there's a developer system with actually 244 CPU cores. And on the right we have a PyTop, which we can also modify to support some boards that are a little more powerful than the Raspberry Pi it's made for. So there have been a couple of concerns given Mandriva back when it was still controlled by the company, had a couple of other ports. There was a short-lived PPC port, there was a short-lived Spark port. They all got discontinued. people are wondering if the same will happen to our new ports, but that's not going to happen because this time under the community control instead of under the company's control, we are doing things the right way. So mistakes that have been made in those previous ports that we are not going to repeat, and that probably nobody else trying to port to new architectures should repeat, is porting without community participation. That was something some companies tend to do, just fork their own product, port it in private, and then at some point make a code drop without involving the community at all. That's clearly not happening this time. Another mistake made earlier was porting an old release instead of porting the current development branch. So they took an old released version that was already considered stable and ported that, while in the other architectures the world was moving on. And by the time the port was done, it was already so far behind that nobody wanted to use it anymore. And it was really complicated to rebase that to newer versions then, because it was already so far behind. So that was another reason why ports got dropped previously. But this time we are doing the right thing and just porting the current development branch, making sure that everything that's being built for the new version is automatically built for all architectures. And the last and maybe biggest point is having separate toolchains for every architecture, separate cross-compilers even, so that in some of those old ports where the cross-compiler was actually a different version of GCC than the native system compiler, which is something that must be avoided where we want consistent results. And of course, architectures that got less attention would fall behind. Like, I think there was one point where we had GCC 4.8 on x86, while we had GCC 2.7 on Spark or so. That's just something that must not happen with the new ports. So, how do we do it the right way? First is getting the toolchains, including the cross-compilers, right. I'll cover that in a bit more detail later. Then build all the core packages that we need to compile the others, which is primarily the toolchain packages and also libraries that are being used by other packages. There's no shortcuts we can take there. There's still some work there that obviously needs to be done. We'll come back to that a bit later as well. Then when the core packages are ready, we add the new architecture to the build system, which means whenever we build a package for any architecture, it's automatically built for all of them. And if it fails on one architecture, it is dropped from all the others, and the person who built the package gets notified that he needs to fix it on that architecture and then submit it again. There's an intermediate step in which we add the architecture to the build system but don't make the build system fail, which is needed while bootstrapping to make sure that it's not a fatal error if a library is not available on the architecture yet. But we are already past that point, so at this point, if a package is built for x86 and fails on ARM, the package is not going into the tree. Next step is trying to build all packages, even the ones that are not very commonly used, and then just making sure all the packages exist for all architectures. Obviously, minus some packages that are architecture specific, like there's not much of a point in building the U-boot bootloader on x86 or grub on RISC-V. So this is what our build system looks like. It may be a bit hard to read in the far end of the room, but we can see a couple of packages that succeeded because all architectures were successful. One where only a couple of tests failed, and then Here we have a package that shows ARM succeeded, ZNVR1 succeeded, ARC64 succeeded, x86-64 failed. So the people had to go back and rebuild that package. So, bigger point was the tool chains that we're going to come back to. We certainly don't want to end up in a situation where different architectures have to use different compiler versions, where cross compilers are out of sync with native compilers. And I'll admit it, we are lazy as well, so we don't like having to update 10 packages containing the same code essentially for 10 different architectures. So we modified our toolchain packages to generate the native compiler and cross compilers for everything else from the same source at the same time. Next, I'll address how to do that. But there's another advantage that comes with this, which is you get cross compilers from any architecture to any other architecture. So while there's probably not all that much reason why you would want to have a 32-bit ARM to 64-bit x86 cross-compiler, we can provide it. And there will be some situations in which even such a strange thing can become useful. Maybe you're just carrying your 32-bit ARM phone and want to build a package to run on a computer. And with the latest versions you can do that. So here's an example of how we did it. We are just adding a line on the top that defines the targets as a list of all the architectures we want to support. You can see that this is actually a few more than I've listed in the presentation title, because we also support targeting different libcs. I mean, our standard libc is glibc, like what everyone else is using too, but we can also support more minimalistic systems that are built on top of the Android libc or Muzzle libc. Then, when we are done with defining the targets, we have a macro for RPM here that expands those RPM-style target names into toolchain triplets. So what you see here is the toolchain name that RPM expects, and this will expand to the toolchain names that the compilers expect. It's a little sad that there's a difference between those. At first we thought it might be better to patch RPM to just use the default names that the rest of the toolchain is using, but then that would have broken compatibility with the versions of RPM used by other distributions, and we decided that it probably makes more sense to have this conversion step in between than breaking compatibility for the sake of having a cleaner solution there. Now, next in that spec file is the usual RPM boilerplate, so I'm not putting that here, that's just what's always there. But then the build process becomes interesting again. Essentially we go over all the targets that were defined in long targets, which is the result of this macro, which is the versions of the toolchain names for the GCC binutils and friends. And then for each of those we generate a subdirectory, put in the configure options and run a build as usual, which means that when we are building the native compiler, it gets built with those options, and all the cross compilers get built with those options, and the result will be essentially all the toolchains we are interested in living in the subdirectory of that build. And then, because, as I mentioned before, we are lazy, we don't even want to write down the package definitions for all of those, so we generate those automatically as well. We again go over that long targets variable and then just have a little script that generates the RPM boilerplate for all the cross compilers. So whenever we want to add a new architecture, it just comes down to adding a new name for the architecture in here, and all the rest is done automatically. So what we noticed next is RPM needed a couple of tweaks to be able to cross-compile properly. RPM does support -- target, whatever, to try to target a special architecture, but then in the next step the system just isn't set up for cross-compiling when -- target is given. So we decided to patch RPM a little to make that better. We are not 100% where we can use RPM -BA, -target, whatever, to just generate a package for the new target. But we are getting there. The first thing was teaching RPM to detect when it's cross-compiling versus when it's just compiling to a sub-architecture of the current host. We found that this piece of code is probably the easiest way to do it. It essentially just creates the smallest possible C code that you can imagine, tries to compile it and run it. If it can run it, we are not cross-compiling. And if it can't run it, we are obviously cross-compiling. Then next, the various build tools that are called from RPM spec files need to be adjusted to make use of the knowledge whether or not they're cross-compiling. Fortunately, in RPM spec files, we don't generally call configure directly, but we have macros for it that also set the directories correctly for the target distribution and everything. So all the spec files already use that %configure macro instead of just running ./configure. And by modifying that macro a little, we can make that more cross-compiler friendly. So in addition to what it always said, which is defining it as configure and then running ./configure, we are now detecting if we are cross-compiling. If we are cross-compiling, we first set package config path so that tools using package config will find the right directories in the cross-compiler directories instead of grabbing the libraries from the system. And then we add extra targets to configure, so the --target and --host need to be set for cross-compiling. --build should usually be automatically detected to be what you are building on instead of the target platform. And then we launch back into the old version of the configure macro that wasn't meant for cross-compiling. It's similar for packages that use CMake rather than autoconf, which is an increasing number of packages. So for CMake, you specify a separate toolchain file that essentially has all those definitions. And you can set the variable CMake cross-compiling to make sure that it doesn't try to run tests that can't be run by cross-compiling. So that's something we insert in the CMake macro. And as part of the RPM package, we just provide those toolchain files for all the targets, which just explain a little bit about the target. So we are targeting Linux version 1, just is an ABI tag that has never moved for Linux. And, we define the architecture, we tell it which compiler is the default. So we like using Clang, but by default we set it to Clang -target with the target. We can also set it to the target GCC on architectures where GCC works better than Clang. So both of those will work. And the same thing for the C++ compiler. And here we just tell CMake to look in the change root environments for the target architecture instead of in the host system for all the libraries it's looking for. So we don't end up linking ARM version of Qt to an x86 version of libpng or the likes. So one problem is we are trying to target some hardware that wasn't even available by the time we started the ports, like RISC-V. We now have a couple of RISC-V ports finally, but they only became available in June this year. And, we started our port in March. We found that one thing you can do, even for the packages that don't cross-compile cleanly, some of them don't because, for example, they have make files that build a build tool and then try to use the tool they just built with the compiler for the target architecture, which obviously won't run if the host architecture is different from the target. We found that QEMU is a good workaround for that. When you build QEMU with the static and target-derived architecture, and then set it up with the bin form and MISC in the kernel, essentially it enables you to run binaries for the target architecture on your host system, whatever both systems are. That will be a little slow, but it generally works well enough to at least get a basic port up until the target hardware is available and you can boot on it and get things ready in the environment that it's supposed to run on in the end. One way to optimize this is when you have a change root environment that's run through QEMU, you can actually replace some binaries in the change root environment that aren't target specific with binaries for your host architecture. So for example, if you have a change root environment that contains RISC-V binaries, and you know that your build process is going to use make and clang and LD, you can just copy the x86 versions of make and clang and LD into the change root environment, and then those will be run in place of the RISC-V versions in QEMU, which is much faster. That is actually using clang over GCC is really a good thing, because if you drop in your GCC binary, it will target whatever architecture GCC has, where clang has all the cross compilers built into one binary, and with the dash target option you get the output you want, even if the clang binary is actually targeting something else. So the last big problem we are facing with new ports is installation. In the x86 world, we generally boot from a DVD or from a USB stick, and we do that using either traditional BIOS or UEFI, but obviously not all ARM boards, and certainly not RISC-V boards have the drives for that when they don't have a BIOS or something that would have a defined boot process. So there's really no universal way you can boot every hardware, but we noticed that a lot of interesting devices have Android support, so we thought that maybe we can pretend being Android, at least for the sake of the bootloader, and it turns out we can. In the AOSP source tree, AOSP is Android open source project, the part of Android that's being released to the public. There's a tool called MK boot image that generates a boot image file just like Android, which essentially contains a kernel, an initRD, and a device tree file. And we found that if you pass that a kernel that doesn't have the Android patch set or anything, it works fine. So we just built our regular OpenMandriva kernel and use that MK boot image from AOSP, pass it our kernel, our RAM disk, the output we want, our device tree file, page size of the target device, and base where the board loads the kernel from, the kernel command line, and then we get a boot image that we can flash with the standard tools designed to update Android. Next thing that you need for installing things the Android way is a system image file, which essentially is an ext4 file system image containing your root file system. But it uses a special compressed format, so just using mkfs is not going to give you something that fastboot will like. But if you look at the AOSP source tree some more, there's a tool called make ext4fs that will generate the file system image from a directory on your hard disk. Unfortunately, that tool is set up to drop all permissions and ownership, and instead set those up in an Androidish way, which means now there's essentially a table hard code into it saying everything that's in /system/bin will be executable. Everything that's in /data will be owned by whatever Android user that's done by default with, and will be readable only to that user. And we are not following the Android file system standards. Obviously, we are following Linux file system standards. So we ended up patching that tool a little to keep the user IDs and permissions of files in the directory instead of overriding them with whatever is in Android's table. And we've made that patch available here. And with that patch, we can go ahead and just run make ext4fs with the standard tools. So this 10G says we want a 10 gigabyte size rootfs. That -k is the option we added to keep user IDs and permissions the way they are instead of overriding them. And then we can generate the system image with the usernames and everything we want. And we can still flash it using the Android-friendly tools. So now that we have a boot image and a system image, we can say fast boot flash boot image, fast boot flash system image to overwrite the system's boot and system partitions, and then we get something that boots. Sometimes there's a problem that the partition layout on an Androidish device can't be changed. A couple of phones hard-coded. In that case, it makes sense to just use Android's user data partition as the home directory on a Linux system. In that case, you still want to generate it using make ext4fs, but you can point it at essentially an empty directory to generate something you can flash to it. Yeah, that's pretty much all I had. So if there's any questions or comments or dog food for Guido.
Thanks for your presentation. I have a question about, well, it's about similar to Debian. Debian has this multi-arc effort where you can have in the same rootfs different libraries for different architectures. So for instance, I don't know if Mandriva supports i386, I guess.
Yes.
Okay. Then for example, you might find somewhere in the internet an old binary that is built with for i386 and it requires i386 libraries. Is it possible to start it in Mandriva nowadays?
Yes. We are essentially using the same system there. So in the x86 file in particular, we have the 64-bit libraries in /lib64 and the 32-bit libraries in /lib. And for cross-compiling stuff, we allow installing the environment for the other architectures in user architecture name, then bin lib, whatever.
One question is about coimmutures. So how do you find out what binaries could be substituted with native ones? Do you have some kind of automation to find out this?
Essentially, there's no automation, but you can pretty much determine it by looking at what the input is and what the output is. Everything where the output is the same, regardless of what architecture is running on, you can replace, and everything where the architecture is running on changes the output is something you can't replace. So, for example, you can replace stuff like ls and make and clang, but you cannot replace stuff like GCC, which has the target.
The question is,
output.
how do you do this? Do you have a database? For example, you set up this root, and then you look into, your, for example, a table and see what you can replace. How do you do this? Or do you do this manually?
Yeah, at the moment it's a manual process. So at the moment we just generate a change root for the target system and then copy over a couple of binaries that we know to make a difference manually. There's a lot more we could be putting in there that would make the builds even faster, but it would be nice to actually have something that would set it up automatically.
I thought you're generating these truths for every build, but if you do it not that often, then manual setup might make sense. But I wish you had something more automatic.
Yeah, that will probably come next time we actually face the problem. Because right now we have boards that natively target all the architectures, and we don't really use the QEMU change roots, but the next time we need to target something new that will come up again, and then we will probably come up with a script that does it automatically.
Yeah. The next question is, how do you make maintainers interested in fixing bugs on those new architectures they don't have any access to? Or do they have any access? How do, besides QEMU, it's very slow. They're probably not very interested. How do you fix this?
That's actually a good question, and we do have people complaining about supporting crappy architecture X, but most people realize that there's a good reason why we support them. I mean, everyone is interested in ARC64 because everyone has an ARC64 based phone these days, and RISC-V is interesting because everyone has seen that it's a completely open architecture, and we just like the idea of being able to modify the processor itself if we even wanted to. And of course, everyone gets at least SSH access to a machine for every target. So it's not like there's some architectures that are completely locked up from everyone or so. But yeah, still there's sometimes a motivational problem, but I think it's one of those things people just have to accept as a chore, just like you have to accept taking your trash out.
Thank you.
Okay, what about other questions? Yeah, we have one. Please.
Thank you. I just noticed that, well, as I understand, you are detecting that you are cross-compiling by compiling a small piece of code and trying to run it.
Right.
I just noticed that this solution is not universal. It probably fits your needs. It's probably perfect to use it, but if you will try to cross-compile for the old CPU that is compatible with your architecture, it probably won't detect that you are cross-compiling, yeah?
Yes, that's true. It's not a perfect solution yet, but there are actually other ways you could do it, like you could run the compiler the same way and then use the object dump tool from binutils or so to detect what the architecture is. But then the script would have to be much more complex to actually detect differences, like, for example, if your cross-compiling to i686 on x86-64, so you actually want it to be seen as native because you can run the stuff and it's then not generally necessary to run it as a cross-compiler. And when it would be necessary to see it as a cross-compiler, even though a simple application might run, like when you're cross-compiling from generic 386 to Pentium 4 or whatever, yeah, then you'd probably need some more checks, but that's not a situation we've run into so far.
Okay. So if we have no more questions. Oh, we have.
Thank you for your work. One question about difficulty. How many time does it take to porting so much software from one architecture to new ones? Thank you.
Yeah, that is a good question. So it has taken us about 4 months to have something that is bootable on RISC-64, for example. On RISC-V it's taking even longer because on RISC-64 there were already a couple of other distributions targeting it, so they had already done the work of fixing up some assembly code that didn't work on RISC-64, so we could benefit a lot from work others had already done. While on RISC-V we are one of the earlier distributions doing it, so there's a lot of packages that actually fail to build because the upstream code doesn't support it yet. So it's a bit hard to tell how long this stuff takes because it depends on circumstances like that, and also on whether or not the particular compilers you want to use are ready already. For example, again in RISC-V, on all the other architectures we use Clang by default because it has all the cross compilers built in, but on RISC-V the Clang just wasn't ready yet and we had to switch to, back to GCC for the default compiler there. So it's kind of different for every architecture, but you can expect it to take anything between 3 months and 3 years.
Good answer. Thanks. I see no more questions, so now we should use the brain of our speaker to decide who will receive a t-shirt for the best question. We have a volunteer with a bunch of t-shirts. Yeah, take them. And what about your guess? You should decide one good question, one question which you liked most of all other questions, and we should give a t-shirt to this person.
Okay, so, since I'm a totally evil person, I'll ask myself how much is 1 + 1, and I'll answer 2, and I get the t-shirt. No, but in fact, I think he probably should get it.
Yeah, I know whom you are speaking about. Having the first talk is a good moment when you can choose your own size. Thank you once again for your wonderful talk. And